All right, people, welcome back. So now we'll tackle the addition method with systems of nonlinear equations. I think maybe your quiz this week might look kind of similar to this. It'll probably also be the last of the quizzes. So that'll be fun. So they give us here now two nonlinear equations, right? They're both nonlinear. We have x squared plus y squared equals to 3, and x squared minus y squared equals to 1. Notice that we have the coefficient of 1 on y squared in the first equation and the coefficient of minus 1 on y squared in the second equation. So if we add the two equations together, the y squareds cancel each other out, right? And so this abides by the same kind of guiding principle that if I have a solution pair to if I have a solution pair to both of these equations here, then it will remain a pair when I add the two equations together. But cleverly enough, when I add the two equations together, I get an equation that just has x's in it. So I get 2x squared equals to 4. And so now I can isolate and solve for what those x values need to be. So we divide both sides by 2. We get x squared equals to 2. So then by the square root property from back in the beginning of the term, we get that x is either the square root of 2 or minus the square root of 2. Okay, so then for each one of these, we will get an equation. We'll plug back into either one. It doesn't matter. So I'm going to plug these back into the first equation and then solve for y. So if x equals to the square root of 2, we get that plugging it back into the first equation, we'll get the square root of 2 squared plus y squared equals to 3. That becomes 2 plus y squared equals to 3. So y squared equals to 1. And then again, by the square roots property, we get that y must equal plus 1 or minus 1. So we see here that we get two different solutions just from here. So we get if x is equal to the square root of 2 and y equals to 1, and x equals to the square root of 2 and y equals to minus 1, or two pairs. So now we'll go and do the same thing when x is minus the square root of 2. But oh gosh, when you square minus the square root of 2, you just get 2 again. So this reduces to the same equation, y squared equals to 1. And so again, y equals plus 1 or minus 1. So in the end, we get four solution pairs. The square root of 2, comma 1, the square root of 2, comma minus 1, minus the square root of 2, comma 1, and minus the square root of 2, comma minus 1. Excellent. Okay, and so then one last example they give us here is an application problem. So we've got a closed box in the shape of a rectangular solid, and its height is 5 centimeters. Its surface area is 94 centimeters squared, and its volume is 60 centimeters cubed. They would like us to find the dimensions of the box. Well, we already know one of the dimensions, the height. So the remaining two we need to know are like the length and the width. So I'll call one of those x and the other one of those y. And in the picture that I've drawn here, I've labeled x and y and 5 in every possible place that they occur. So we have these lines are length 5, these guys are length y, and the front and back are length x. Okay, so what do we know? Well, the volume of this box you can compute by taking the area of the base rectangle and multiplying by the height. So that gives us 5 times x times y. And then the surface area of the box you get by just adding the areas of all 6 pieces that go into this box here. So we have the sides of the box are each an area of 5 times y. So we get 2 of those. Then we have the front and back of the box. Those are each an area of 5 times x. Okay, so we get 2 of those in our surface area formula. And then we have the top of the box and the bottom of the box, and those are each area of x times y. So we get 2 of those contributing to our surface area formula. So when we clean that one up, we get 10x plus 10y plus 2 times x times y. Okay, and what they've told us then is that the volume of the box is 60, so we get 5xy equals to 60, and the surface area of the box is 94. So then we get 10x plus 10y plus 2xy equals to 94. Okay, So then I'm going to try to solve this maybe by substitution, just because that's kind of the method that I like the best. And I don't really see any totally clear way to do it just by addition. So one thing that I notice is that I can simplify the first equation a little bit by dividing both sides by 5, and I get x times y equals to 12. That's nice, because in the second equation, I see the expression x times y. And I can simplify that by just importing the number 12 right into that spot there. That's very nice. Another thing, I can go a little bit further and take x times y equals to 12 and solve for either x or y, right? So in this physical context of this problem, we know that the numbers x and y need to not be 0, right? Because we won't have a box if x or y is 0. So we can safely divide by either one of those. So I'm going to divide by x and solve and get y equals to 12 divided by x. Okay, but so maybe I'll use that in a little bit. But the first thing I'm going to use is just this one piece, xy equals to 12. I'm going to plug that into this second equation here to simplify it a little bit. I get 10x plus 10y plus 2 times 12 equals to 94. And then from here, we can subtract the 24 from both sides, and we get 10x plus 10y equals to 70. Now here you might be thinking, oh, this is very nice. Maybe I'll annotate a little bit here for a second. Maybe we can divide both sides of this equation by 10 now and get something like x plus y equals to 7. I think that's pretty nice, right? So you got a couple of choices now at this stage of the game. So we could take this new equation that we've got, x plus y equals to 7, and solve it for either y or x, and plug that guy back into the first equation to get an equation with just one variable. So since that's not really how I filled these notes out, I'm going to do something a little bit differently. But note that you kind of don't always have like one correct path to get to the answer in these kind of problems. So you can kind of just do whatever's clever and make sure that you don't do anything illegal. Okay. Okay. So continuing on, I'm going to take the point of view that I was kind of following up here before I got a little sidetracked, is that if x times y equals to 12, then y equals to 12 divided by x. Okay. And so I've got this equation, 10x plus 10y equals to 70. Well, I'm going to plug y equals to 12 over x into the y part of this equation and see what happens then. So we get 10x plus 10 times 12 over x equals to 70. Okay. So then we get 10x plus 120 over x equals to 70. And if I get a common denominator on the left side, that would be x. I'll get 10x squared plus 120 all divided by x equals to 70. And now I can multiply both sides by x to get that out of the bottom down here. And I get 10x squared plus 120x equals to 70x. Okay. And now I think I've got a nice quadratic equation, right? 10x squared minus 70x plus 120 equals to 0. And it looks like all the coefficients of that guy are multiples of 10. So I can divide both sides of this equation by 10 and leave myself with the nice quadratic equation, x squared minus 7x plus 12 equals to 0. Okay. So this guy factors as two numbers whose product is 12 and whose sum is minus 7 are minus 3 and minus 4. So then x equals to 3 or x equals to 4. Okay, so now we've got two possible cases for x. What are the corresponding cases for, or the corresponding values of y? So let's see, when x is 3, y is going to be 12 over 3, which is 4. Or when x is 4, y will be 12 over 4, which is 3. So really what this kind of says in effect is that we only were able to solve, like we don't know exactly which one is x and which one is y. We just know that one of x is 3 and the other is, like one of x or y is 3 and the other one is 4, right? So this kind of symmetry in the solution is kind of bore out by the fact that we don't exactly know which one's which. We could have either or. All right, so that settles that. So when we come back next time, we will start the last chapter of the textbook. which is about matrices and how they relate to this conversation about systems of equations. So we'll see you then.